morning, friends. I warm welcome to all of you in this lecture series of Mechanics of Solids, and today we are going to study about bending stress. Up till now, in the previous series, we learnt about the concept of bending stress. We learnt from the previous session about the types of supports, types of beams, types of loads acting on the beam, determination of support reactions, plotting of shear force and bending moment diagram of statically determinate beam. Also, we have studied the concept of bending stress and section modulus, concept of bending equation and moment of resistance. So, today's objective of this session is that after studying this session, you will be able to draw the bending stress distribution diagram and calculate maximum bending stress in a given beam, calculate the bending stress with symmetrical and unsymmetrical sections. Now, let us revise some of the things that we have studied in the previous session, and then we will proceed further today by the solving of several numericals using the concept of bending stress. If we take any section of a beam and consider the free body diagram on either side, we find that there must be the three internal stress resultant at the section in general to maintain the equilibrium of the free body. These three are bending moment, shear force and axial force. Here in this topic, we are discussing the effect of bending only. See, refer the figure. The beam, simply supported beam subjected to the external loadings. Now, if we take a section XX and let us consider only the left part of this particular beam, then at a section the three internal resisting forces will be developed. The name of these forces are bending moment, axial force and shear force. Now, this bending moment generate the compressive forces at a section on top layer, while tensile forces at the bottom layer. This generate the stresses. That stresses are known as bending stresses. Hence, under the effect of lateral loads, the beam bends and the longitudinal axis takes a curved shape. The beam produces an internal resisting couple to balance the bending moment due to applied loads. This couple is generated by the normal compressive and tensile forces in the section. Refer the figure. Because of the external application of load, the compressive stress and here bottom section tensile stress will be developed. Now, there will be a certain causes to create this one. There will be certain causes for beam deflection. Also, we have studied up till now in the previous session about the bending equation. We have derived the bending equation. That equation is m over I is equal to f over y is equal to E over r. M is nothing but the moment of resistance of a section, I moment of inertia, F bending stress at a particular section, Y the depth at which we have to find out the bending stress, E modulus of elasticity, R radius of curvature. Now, what is section modulus? Section modulus is defined as the ratio of moment of inertia of a section about the axis to the outermost layer from the neutral axis, that is z is equal to I by y max, where I is the moment of inertia, y max is the distance of the outermost layer from the neutral axis. We have also derived the equation, that is m is equal to f max multiplied by z, where m is the moment of resistance offered by the section, that is it is the maximum bending moment. Also, moment of resistance offered by the section is maximum when the section modulus is maximum. Hence, section modulus represents the strength of section. We have also derived the four different equations of section modulus for rectangular section, hollow rectangular section, circular section and hollow circular section. So, if we take the first one, that is rectangular section, then the z is equal to bd square by 6, where b is the width of section, d that is the depth of section. For hollow rectangular section, z is equal to 1 by 60 bracket bd cube minus small bd cube, while capital B is the outer width of hollow rectangular section, small b is the internal width of section, d overall depth of section, while small d is the internal depth of section. For circular section, the section modulus pi by 32 d cube, while d is the diameter of section, while for hollow circular section, z is equal to pi by 32 d bracket capital D raised to 4 minus small d raised to 4, capital D outer dia, small d inner dia of the section. Now, before we proceed further about the problem 1, that is the solution of a problem to find out the bending stress, in the previous class we have started one problem to find out the section modulus for a T section. So, let us go to the tabletop and let us check it out whether you have obtained the same answer for a T section for a section modulus or not. So, the previous session, please on the tabletop, we have taken a one simple problem of a T section. This is the section which we have taken in the previous lecture. And our intention is to find out Z, that is a section modulus. Now question, all dimensions are in terms of millimeter. Now, how to find out the Z for this particular section? Now, to find out the value of Z, we know the formula Z is equal to I by y max. So, I have to find out I as well as y max. To find out the y max, it is at most important for me to find out the CG of a section. So, what I have to do? I will divide this T section into the number of known parts, number 1 and number 2. Let this is my neutral axis, let this will be the y, that is the bottom, hence B, let this will be yt. Now, I have to find out first the location of neutral axis. I have drawn, that is of randomly. I have to find out the value of yb, value of yt, and then I can plot the neutral axis. So now using our basic concept, yb is equal to, we know it, a1 y1 plus a2 y2 divided by a1 plus a2. Now the question here is, what is a1? a1 is the area of first part. What is the area of first part? That is 100 into 10, area of first part, multiply by y1. Now we have taken bottom, so this is my reference axis. This bottom layer is of my reference axis. Then what is y1? y1 is the distance of the center of first part to the bottom layer of T section. Now see, this distance is of 100 mm. The CG of first rectangle is over here. So we know this distance is of 10 by 2, that is of 5 mm. So this distance is of 100 plus 5, 105. This is our y1. Now let us go for a2. What is a2? a2 is the area of the second part, which is also remains same, 110, that is 100 multiplied by 10, that is a2. Now multiply by y2. y2 is the distance from CG of the second part to the bottom layer, that is of 100 by 2, that is of 50, divided by a1 plus a2, 100 into 10 plus 100 into 10, and when you simplify this simple equation, we get it out, the yb as 77.5 mm. So if I will redraw my figure on this next page, please observe over here on this tabletop. This is my neutral axis that I have got it, and this distance I got as 77.5, and this is nothing but my yb. Then yt is of this one. Total depth is 100 plus 10, 110 minus 77.5, that is of 32.5 mm. Now we got yb, we got yt. So now next intention is to find out I value. This is of 100, this is 10, this is once again 100, this is 10, as I divide into two parts. So this is one of the composite section. We know how to find out I. The basic formula to find out I is, that is the formula of the rectangular section plus a into h square. So I for this first rectangular section is 1 by 12 bd cube, because I found out ixx, this is my xx axis. Then 1 by 12 b d cube, this is the I for the first rectangular part about these axes. Now I have to convert it this to this axis by plus this term a h square. A is the area, that is 100 into 10 multiply by h. H is the distance of the CG of the first area to the neutral axis. So this is my h for this one, this is called h1. This is h1, and that is nothing but total is 32.5 minus 5 square. So this is the contribution of I from the first rectangle. I have to go for another rectangle plus 1 by 12 BD cube. B is 10, D is 100 cube plus A H square. A, that is we know 100 into 10 into H square. The CG of the second part is over here. So this is my H2, that is of 77.5 minus 50 square. So when you simplify this, you got some value of I in terms of mm raised to 4. I think you can solve by using the calculator easily. Now we know that Z is equal to I by Y max. You got the value of I from here, so you know the value of I. What is Y max? Y max is nothing but what is the maximum value from YT and YB? Definitely it is YB. So here it is 77.5, and you whatever the answer you got, it is in terms of mm cube. This is the value of Z for this T section. So I wish that you can easily understood how to found the value of Z for a given I section, T section or any other section. So with this, let us proceed further for the first problem of bending stress foundation. So problem number 1. A steel plate of width of 120 mm and of thickness of 20 mm is bent into a circular arc of radius of 10 meter